So last time I was done with matroids. Today I'm going to do oriented matroids. And yeah, it's a bit unfortunate that I have 2 lectures left for these things, because these are like my favorite kinds of matroids. But yeah, I'll try to say as much as I can. And for you, yeah, I mean, you guys are already experts on matroids and vectors and polytopes, so this should come naturally to you, basically. So what is an oriented matroid? Let's say first of all, if I take a graph, right? I take a graph, maybe something like this. A, B, C, D, E, F. Then I can construct the oriented matroid, right? So for example, I can consider the circuits of the unoriented, of the usual matroid. Circuits of the usual matroid of G, which are, can you tell me the list of circuits for this one? A, B, C, D, E, F. Okay. Now let's suppose instead that I have a directed graph. So maybe I'm gonna, when I have an oriented something, I'm gonna put an arrow on top of it. So, and the graph is gonna for me mean directed graph. So let's say I draw the same kind of graph, but now I just choose some arbitrary orientations, like this. Also A, so now my edges are oriented. Now, how I want to define oriented circuits, such a graph. Let me call them signed circuits. And these are going to be, yeah, so basically I want to take the same circuits as before, A, B, C, and D, E, and F, and then I'm gonna, for each of these elements, I'm gonna put either a plus or a minus. And the way I'm gonna do that is I'm gonna take my circuit, and then I'm gonna traverse it in one direction, and then I'm gonna look at which arrows point in the same direction and which point in different directions. All right, so for example here, what would I do for A, B, and C? A, B minus C, plus, plus, and minus. Or I could, I mean, there is no canonical, I mean, for planar graphs, there is the clockwise and counterclockwise, but in general, if I have a circuit in some graph, then I could equally well choose the opposite orientation. And similarly for D and E, what do I get? All pluses or all minuses? Plus or minus. Okay, so that is going to be my list of signed circuits for a graph. And okay, now what about vector configuration? Let's say I have a vector configuration as usual. And then what are the circuits of the corresponding unoriented matroid? What, just by definition, what is a circuit of that? Nice. Yeah, it's a minimal dependent set. So let's say C. Here the ground set E is just bracket n. And then let's say C is a circuit of my usual matroid. Then there is a linear dependency. Minimal sum over I in C, AI VI is equal to 0. Sum AIs. And this is a minimal minimal linear dependency between these vectors. So now I want to do something like this. I want to each element of C, I want to assign either a plus or minus. How do I do that? Okay, I see. So indeed, I should look at the sign. Look at signs of AIs. First of all of these coefficients are non-zero because it's a minimal linear dependence. Second of all, don't I have some choices for the AIs? Do I have choices or do I not have choices? Yeah, I can basically, the only freedom I have here, because it's a minimal linear dependency, the only freedom I have is just rescale all AIs by the same number. So if it's positive, the signs are the same. If it's negative, I get basically negatives of all the signs. So yeah, maybe I should try an example. Yeah, have some instructive example. V1, V2, V3, and V4, and maybe V5 is here. So let's see. I have these linear dependencies. For example, V1 minus V2 plus V3 is 0, or I guess there's another one, V1, V2, and V4. V2 plus V4 is 0. There's also V3 minus V4 is 0. There's also V5 is 0. So these are my minimal linear dependence. In some particular, from that picture, I would get the signed circuits. Of course, here all the coefficients are 1. In general, they could be some other real numbers. And yeah, the signed circuits are the 3, 1. These are the unoriented circuits, 4 and 5. Then I either put plus minus plus or minus plus minus. Here I'm going to put, again, plus minus plus, minus plus minus. And here, yeah. So basically, I want to record that data. That data is going to be my oriented matroid. And yeah, so I need to introduce some terminology. Previously, I was dealing with just sets. Here, I'm going to be dealing with signed sets. So it's just going to be a bunch of definitions. A signed set is a pair C, C plus, C minus. It's a pair of disjoint sets where C plus, C minus are subsets of my ground set as usual, and they're disjoint. And so for example, here I would have the first set would be 1, 3, comma 2. This is how I would write down a signed set of this form. Okay. And so here's some more terminology. For example, the support of a signed set is just the union of, it is denoted C. Yeah, I'm gonna denote unoriented versions of things by underlining them. That's the support of C, and also there is the negative of C, negative, which is this operation here of changing all the signs, which is negative C is C minus comma C plus, and there's also going to be the 0 kind of the empty. The 0 sign vector means just you assign zeros to all numbers in your ground set. Just by definition, it's empty set comma empty set. So I'm kind of going to think of C as assigning signs to all elements of E, and outside the support is just going to be 0. So I'm going to denote by plus minus 0 to the E. It's just the set of all signed subsets of E. And by the way, plus in general, it's an abbreviation for +1. Minus is -1. So I can multiply these things together and get a well-defined sign. All right, so that's basically all the terminology I need to define oriented matroids. Any questions so far? Okay. Definition. An oriented matroid is, well, by definition, again, there's going to be many different objects you can use to define oriented matroids. For me, for now, it's going to be a pair M, E, C, where so E is a ground set as usual, and C is a collection of signed vectors. Plus, minus 0 to the E. So that's going to be my collection of signed circuits of a matroid. And it has to satisfy a bunch of axioms. And of course, the first few are going to be trivial. So the first axiom is that the 0 vector is not a signed circuit. The second axiom is that if you have a signed circuit, then the negative of a signed circuit is also a signed circuit. And finally, yeah, maybe you could tell me what should be the interesting axiom. Let's say if you think about graphs. First of all, what's the usual axiom for graphs? Do you remember like for unoriented matroids, what's the okay. Yeah, so if you have two circuits which have an element in common, something like this, 2, and this is C1, and this edge is E, then you can eliminate this edge. There is a circuit which is contained inside the union of these two without the edge, without the extra edge. So what's the oriented version of this axiom? I see. Okay, yeah, so what you want to say? Yeah, I see. All right. So you're saying basically if I have one, let's say they're all oriented positively, all signs are plus. And let's indeed assume that E appears in, yeah, that's actually, okay. Okay, I see. No, that's almost exactly what I'm going to write down. So let's say you have two circuits, C1 and C2, and well, actually, hold on. The second axiom is also trivial. Hold on. Yeah, there's one more trivial axiom. If one support is contained inside the other support, then C1 is plus or minus C2. That's the stupid axiom. Okay, but the interesting one. Okay, C1 and C2 are two circuits, and let's assume that C1 is not the negative of C2. And let's say E is oriented into circuits in the opposite way. So E belongs to C1 plus intersect C2 minus. Then I do want to eliminate that edge. I want to take some sort of weird union of two circuits and then eliminate the edge from the union. And the precise statement is that there exists another circuit, C3, such that C3 plus is contained in the union of two plus, of C1 plus and C2 plus without E. Then C3 minus is contained in C1 minus union C2 minus without E. So in some sense, the picture you should think of is you have this edge, which is traced in opposite directions by the two cycles, and then the C3 cycle you get kind of agrees with all these edge orientations. It doesn't use the edge E, but on the other edges, it agrees with each of the two cycles. Well, one of the two cycles. Yeah, so that's basically the definition of an oriented matroid. And you can similarly think of, maybe I should look at this example. Let's say, yeah, let's try an example. That's actually interesting. Let's try a different example. So I'm going to draw some example, and then you're going to tell me how to eliminate an edge from two circuits. Let's say my example looks like this. Zero, V1, V2, V3, V4, and V5. Okay, so I have a whole bunch of, let's say I take two circuits. V1 minus V2 plus V3 is 0, as you can see, and also negative V3 plus V4 minus V5 is 0. Okay. So in the context of this axiom, C1 is 1, 3, 2, and C2 is 4, 3, 5, and E is equal to 3. So you see that E appears in these two circuits with different signs. And okay, now what do I do? How do I find C3 from these? Okay, I can add the two equations. Nice. V1 minus V2 plus V4 minus V5. Okay. So is C3 just given by 1, 4, 2, 5? Does that work? That's not a circuit. Right. It's a circuit in 2 dimensions. The circuit contains at most 3 elements. So that's actually this is an honest linear dependence, but not minimal. Not a circuit. And if I just look at if I apply the axiom literally, I need to take the union of C1 plus and C2 plus minus E. C3 plus is a subset of the union of these two without the E, without 3. Subset of 1, 4. E3 minus is a subset of 2, 3, 5 without 3. It's 2, 5. So does there exist a circuit? V5 is negative V1. Oh, nice. Does it work? 1, 5. Yeah, actually. 1, 5 is the only one that works. Well, actually, 1, 5 is not a circuit. I don't know if you can notice this. Is this a circuit or not? Not a circuit. Not a circuit. 5, empty set is a circuit, but it's not of this form. Cool. 1, 4, 2. Interesting. E3 is equal to 1, 4, 2. 1, 2, and 4. Right, yeah, so 1, 4 is in C3 plus, and 2 is in, yeah, this actually is a subset, and it is indeed a circuit because, well, what you can do is you can take this equation and use that V1 is equal to negative V5, or the other way around. V5 is equal to negative V1, and you can just plug it into the equation. And then you get twice V1 minus V2 plus V4 is 0. Indeed, this is a circuit. And is there another one that works? Or is it the only one? Four, 2, 5. 4, 2, 5 also works. Indeed, 4 and 2, 5. Yeah. So these are the only two that actually work. Yes. But the good news is that the axiom seems to work, and you can check that in general. If you have two linear dependencies which use this with opposite signs, you can add them up with coefficients to eliminate this guy, and then you get some linear dependency. It must contain a minimal linear. It must specialize to some minimal linear dependency. But you have to prove it. There is. What? Thank you. Yeah. So let me just make this precise. If you have a vector configuration, v1, vn, r to the d times n, then the corresponding oriented matroid, the circuits of the corresponding oriented matroid of V are just all sign vectors of minimal linear dependencies in V. So that's the definition of the vector configuration matroid. And of course, if you have it as definition number 1, if you just state these things precisely, if you have a directed graph, directed graph, then the corresponding oriented matroid is defined as the circuits basically C plus, C minus, as you take collections of edges such that if you swap the orientations of the edges in C minus, you get an honest oriented circuit or oriented cycle. Reorienting edges in C minus gives a directed cycle on the support. All right, so now if you have any directed graph or any vector configuration, you get an oriented matroid out of those. And then now I'd like to compare like which things for usual matroids hold for oriented matroids and which don't. I want to extend the theory from matroids to oriented matroids. Maybe I should give the axiom. So one thing that works pretty easily is deletion contraction. Which for usual matroids, we did it in the language of basis and independent sets. Here, let's try using circuits. Let's say you start with an oriented matroid. And then I want to choose an edge E, well, an element of the ground set. How do I delete an element from my matroid? What's deletion? Yeah, let's say in terms of, so far I'm only dealing with circuits. Take the circuits that don't contain E. All right. Yeah, so first of all, E has to not be a for loop, as usual, of the, yeah, I guess, let me denote by underline M, the underlying matroid of my oriented matroid. So if E is not a call loop, then M without E is you just take all circuits whose support does not contain E. Okay, what about contraction? Let's say E is not a loop of my matroid, of the underlying matroid, let's say. This is supposed to be circuits. You make it a loop. All right. You make E a circuit. Well, I want my ground set to decrease. I want to actually get rid of E from the ground set. Okay, interesting. So I take, well, what if they don't contain E? Let's see. Okay. All right, so let's try that. So C plus without E, C minus without E, where C is just any circuit. does it work for graphs? I see. So if I have some cycle in my graph, and then E somewhere is a chord of that cycle. If I contract E, my cycle splits into kind of two different cycles, right? Yeah, it doesn't quite work, right? Because you can't just keep all these other cycles as is, because they're going to split. But this almost works. So what you actually need to do is you need to take E, contract E, are minimal by inclusion elements in this set. So you take all cycles, and then so basically when you get rid of E, you either get some garbage linear dependencies which are sort of redundant. But if you just take minimal by inclusion ones, for example, here, if E is oriented, then this guy is a cycle, and this guy is also, I mean, these two are separate oriented circuits. And those, if you throw away E from those, they're going to give you these two circuits. So this somehow taken minimal by inclusion just works. And you get circuits of the contraction. But you can see that here, usually contraction and deletion are quite easy for matroids, but here somehow contraction is more complicated than deletion. Wonder why that is. Okay. So yeah, there is an exercise that these are both oriented matroids. You have to do at home. All right, but okay. So what about, aren't these dual to each other? What's the deal with the duality? Which for usual matroids, right, it was very easy. You just take complements of all bases. And what do you do for circuits? That's actually tricky. Circuits of the dual matroid. So let me write down what's going on. So first of all, if you have introduce some notation. We have a sign vector, C plus, C minus, and let's say E belongs to my ground set. Then I'm going to denote by C of E is going to be either plus or minus or 0, depending on whether E belongs to C plus or C minus, or doesn't belong to the support. And then I'm going to introduce the notion of orthogonality for sign vectors. Let's say I have two sign vectors, plus, minus 0 to the E. I want to write X orthogonal to Y. So here I could make several definitions. And I don't know, maybe, do you want to guess what the definition is going to be? What are your suggestions for orthogonality? Okay, if their supports don't intersect. That is true. Or, very nice. Okay. Or there, yeah, that is correct. So there exist two elements, E and F, which are oriented by X. So E is oriented the same in X and Y, and F is oriented in opposite way. Yeah. So yeah, I guess it's a little different. I should do X of E equal to Y of E, and X of F equal to negative Y of F. All right. So in other words, you should think of orthogonality as kind of there exist two actual real vectors with these sign patterns, which are orthogonal. Basically, so that if the supports are disjoint, clearly they're all going to be orthogonal. But otherwise, here, yeah, your vectors are going to, in the dot product, there is going to be a positive term and a negative term. Okay, now let me, so to talk about the dual matroids, I need to introduce another notion. And it's not going to be basis or independent sets. It's going to be what is called covectors of an oriented matroid. By definition, they're denoted by L of M. And you just take all sign vectors which are orthogonal to your circuits. For all circuits. So this is I mean, certainly you can do that, right? You can take all circuits, and then you can go through all possible sign vectors and only keep the ones which are orthogonal to every circuit. But what does this mean? What is the, let's say my matroid comes from a vector configuration. Try that. Maybe I don't need circuit elimination. Let's say I have a vector configuration. And I take the corresponding oriented matroid. How do I, what's the interpretation of these covectors? There is a simple natural interpretation of them. Any guesses? All right, yeah, so this one's actually tricky. I mean, it's going to be natural, but sort of. Well, let's assume that these vectors span R to the D. Yeah, that's my running assumption, by the way. All graphs are connected, all vectors span the ambient space. All right, so let me actually write it down. So let's say you take a vector in R to the D. Then I can, let me denote by epsilon I of H, the sign of the dot product of H and VI. So that's an element of plus minus 0. Let me note by epsilon of H, just epsilon 1 of H, etc. epsilon n of H. This is an element of, it's a sign vector. E is bracket n in this case. And that's it. These are all covectors. Claim covectors of M are all vectors of the form E of H, epsilon of H, where H is just runs over all possible, I guess it runs over linear functions on my space. So the picture you should be looking at is I have some vector configuration. So I have R to the D, and I have some vector configuration, and then I choose a vector H. So I'm going to have a hyperplane, which is perpendicular to H. And then here's the origin. So H points, let's say, in this direction, orthogonal to the hyperplane. And then some vectors are going to be in the hyperplane. So maybe v1 and v2 are going to stay inside the hyperplane, and maybe also v6 is just 0. Then maybe, okay? All right. And then maybe some vectors point in this direction, v3, and some maybe point in the opposite direction, v4 and v5, something like this. Then the corresponding epsilon of h is going to be 1, 2, 3, 4, 5, 6. What is it going to be? Zero, 0 plus, minus, minus 0. Very nice. Yeah, so this sign vector belongs to my covectors. And but one other thing I could do is I could kind of rotate this hyperplane a little bit around this axis to make, let's say, I could make v1 on one side and v2 on the other side of the hyperplane. And so I would change h a little bit. Then maybe that's going to be h prime. And then 1 becomes positive and 2 becomes negative. So 3, 4, 5, 6. I would have plus, minus, 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 0. That also belongs to, also is a covector. So covectors are not necessarily minimal. They're just all possible sign patterns you get from you just draw any hyperplane and look at what's on one side and what's on the other side. These are covectors of the corresponding vector configuration. And yeah, it's an exercise to check. Well, an easy exercise is, why is every covector orthogonal to every surrogate? Maybe you can tell me in this sense of orthogonality. Right. Okay. All right. So indeed, if a circuit, a signed circuit, gives me a linear dependency, right? So it's something of the form sum of ai vi equal to 0. And then if I take the dot product of each vi with h, the sum in C of ai HBI is 0. So these dot products are the signs of my covector, and the AIs are the signs of my circuit. And because the sum is 0, that condition of orthogonality has to be satisfied. Either the supports are disjoint, or there has to be a positive term and a negative term. Say the question again. So in this picture, if I take a circuit, what? Okay, yeah, okay, I see. So you're saying, well, actually, if you want to think of paths from the origin to itself, you kind of choose an order in that sum. In particular, like, let's say, maybe v4 is negative v3. Then you can go v3 and then v4, or you can go v4 and then v3. In general, if you change the order of the summands, you can either cross this plane or not cross for each given circuit. But if you just look at these vectors, kind of v3 and v4, either there's going to be one vector on one side and one vector on the other side, or all vectors are going to be inside the hyperplane. Thanks. Okay. All right. So now that I mentioned that these covectors are not minimal, what happens if I take minimal ones? And that's going to be called cocircuits. Take C star M, which is the set of minimal non-zero covectors. Of my matrix. And yeah, maybe I should try another example. Let's say I draw a picture for you, and then you tell me all the circuits. V1, V2, V3 is negative V2, and V4 is here, and then V5 is here. What are the circuits of the corresponding oriented matrix? Okay, H is vertical. Oh, H is vertical. Then the hyperplane looks like this. No, plus minus plus 2. Okay, yeah, let's just write 2, 4, 3, right? Yeah. Okay, 2, 4, 3. Okay, my hyperplane looks like this. 1, 4. H is perpendicular to V4. 1, 2, 3. Is that it? Also the negatives. Okay. I could replace H by negatives. Yeah, so you just kind of draw all possible hyperplanes through like codimension 1 elements of your codimension 1 flats, basically, of your matrix. And those are going to give you cocircuits. And of course, the theorem here is that for each M oriented matroid, these cocircuits are circuits of the dual matroid, dual-oriented matroid, which is denoted M star. So basically, this theorem tells you that cocircuits satisfy circuit axioms. These are just circuits for some dual-oriented matrix. That's the claim. So just to reiterate, you take your original circuits, and then you look at all minimal vectors which are orthogonal to all your circuits. These are going to be the dual ones. Yeah, I'm out of time, so I'll see you all on Friday, which is going to be the last lecture.